Kids! Hi. I am going to do a little instruction video about springs and how do you find the force from a spring and how do you find the energy stored in a spring. So get prepared. So hey, I got a couple springs here. Hopefully you guys did a lab like this where you had a spring and you probably like attached different masses to it. But I can just show you if I have a spring scale here. And if I was to hook this spring scale up to this guy and pull it, you can see as I pull it, do you see how the force gets more and more and more and more? Whereas same thing with this guy, it's just that this guy's a way looser spring, it's not very stiff, so the force doesn't really change very much. But you can see it does change a little bit, but it doesn't change very much because it's not a very stiff spring, okay? Or if you like, this one has a bigger spring constant, more on that in a second. This one has a smaller spring constant. Hopefully you remember from the lab where you guys made a graph that looked like this. Force of the spring and displacement. And when you graphed it, you should have gotten a line, because it is a linear relationship. And then you should have found the slope of the line. So well, how do we find slope? Well, slope is just rise over run. So if I do my rise, force of the spring, if I do my run, my displacement, I get this. And this has physical meaning. It had a physical meaning of spring constant. The spring constant means something. Okay, if you look at the units, it should make sense. The units for spring constant are going to be newtons per meter. So literally what this means, the spring constant, it would be like, let's say for example, I had a spring constant of 20 newtons per meter. That would mean if I was to stretch a spring 1 meter, it would exert a force of 20 newtons. Now this guy is going to have a way bigger spring constant than 20 newtons per meter. This guy might have something like that, for this guy, it would be probably more like 100 newtons per meter because it's going to be really stretched out. But this tells you how stiff the spring is, okay? So that, but it really is, it's why it's called the spring constant. Okay, it's constant for a given spring. But if you look on the formula sheet, this is not how it's written on the formula sheet. It's written on the formula sheet like this. Force of the spring equals Kx, where they have little absolute value signs like this. They have little arrows like this. The arrows are there to remind you, hey, these are vectors. Oh, I should probably make sure you guys understand displacement. This is the displacement. Hey, if you look, here's where my spring is starting. Everybody see it? And then, although it looks like but whatever, you get the idea. And then if I hang this on here, okay, so it stretches out. This is where my spring is ending up. So that little thing right there, that would be my displacement. Okay, that would be my displacement. But what this is trying to show you with these absolute values is, you know what, don't worry about direction. How are you going to get direction? Well, you're going to draw a picture. You're going to draw your FBD to get your direction. But this is going to tell you about the magnitudes. So there's that first piece. The second piece, which is really important as well, is how do you go about, let me make sure, okay, good. How do you go about finding the energy stored in a spring? Well, that's pretty easy. If you go back to our graph and you think, okay, so energy, let's see, energy is related to work. All right, yeah, energy is related to work, so work is equal to the change in energy. So if I'm talking about energy stored in a spring, I'm talking about potential energy. Well, if I have a graph and I have force and displacement and I want to find work, what do I have to do? Well, I have to find the area of that, okay? So like if I go like this and say, hey, I want to find the area of this, which would be like, hey, if I was to have it go from 0 displacement to here, how much work is done? Remember, you might be thinking, oh, well, work is just force times distance. But remember, that formula only works. It works. All right, sorry. This equation only works if the force is constant. And obviously here, the force not constant. So no worky that equation. So you have to find the area. So like, well, how do we find the area? area, that's a triangle, isn't it? Oh yeah, that is a triangle. Well, area is going to be 1/2 base times height. So if we do that, 1/2 base, x, times height, which is force of the spring. But we just said the force of the spring is equal to k times x. So I get 1/2 x times k times x, which means 1/2 kx squared. And that is how you find, if you look on your formula sheet, that's how it's written there, because that's how you find the energy stored in your spring. Now, I want to make sure it makes sense, guys. Let's say you're going from 0 to here, and then you want to stretch it a little bit further. So I'm going to go, here to here. Okay. You got to just be careful with what the question says. If the question says, hey, going from this point to this point, how much work was done? Well, that's just that little bit of area. Okay? Or if it says going from here to here, how much work is done? It's that whole area. So there you go. Bye, kids!